So today we're going to continue with Chapter 7. You can see the sections that we've already covered, mostly SN2 reactions and things related to SN2. Now we're going to start looking at more closely at the elimination reactions, which produces alkenes, and we're going to look at regiochemistry and stereochemistry of the E2 reactions. Now the best thing that you can do is continually go back and review that video that I made for you that discusses and compares SN1, SN2, E1, and E2 reactions. And so in particular, right now, you'll be wanting to look at SN2 and E2 reactions, but we have also touched on SN1 reactions a little bit, and we will look at E1 reactions down here in the next video. But you will want to have a preview of these because you're going to have to be able to retain all of this information in your head. You're going to have to be able to understand very intimately, thoroughly, the differences between these reactions, SN2, E2, SN1, and E1 reactions. And the best place to see them compared is in that video that I created for you, where all of the reactions are drawn on one page. So stop this video and go back and review those before you watch this video, if you haven't reviewed it just in the last few moments. So here we go. We're going to be discussing E2 reactions. So E2 reactions are a little bit similar to SN2 reactions in that an E2 reaction is one step. It is two molecules coming together, just like an SN2. So it's two molecules coming together. So that means it's second order. That's why it's 2. And it produces an alkene. That's why it's elimination. So you are eliminating H and X to create a double bond. This generally happens when an alkyl group bearing a good leaving group, such as a halide. That's why we're studying alkyl halides here, because the halides are good leaving groups. So it's treated with a strong base, so it can undergo this elimination reaction, eliminate H and X, where you have the leaving group at the alpha position and a proton at the beta position. So this comes in, plucks off the proton, the pair of electrons in the carbon-hydrogen bond moves in, forms the pi bond, and then X departs with a pair of electrons, as you can see over here. Okay, so a strong base will react in a concerted mechanism. This is concerted, one step, and so you're going to have to understand what is strong base. And you remember the anion stabilities, REO, that you saw in Chapter 3. Generally, for these purposes, though, it's going to have to be really strong. And very often, these bases will be oxygen anions or nitrogen anions. Those are anions in which the negative charge resides on oxygen or nitrogen. But it's not always, it's not exclusively oxygen or nitrogen. But those are the most common ones, and you'll see that. So you should be easily able to recognize these. E2 elimination is concerted, as we already said. The rate is the rate constant times the concentration of the alkyl halide times the concentration of the base. So the rate is proportional to the alkyl halide times the base concentrations. And so you can see what it is it's related to the frequency with which these two molecules just collide. And so they have to come together, bump together, to cause the reaction to occur. And so it's going to be dependent on the concentrations of these two molecules, of course. And so it's two molecules coming together in the rate determining transition state. So it's second order, E2. So, an oxygen anion. It can function as a nucleophile, but if you have an alkyl, say halide, or an alkyl group that bears a good leaving group, that's what Lg stands for, and this is a tertiary alkyl halide, hydroxide will not function as a nucleophile in this case. So this would be like T-butyl bromide, where you have the T-butyl group. Here, O- will not be able to get in to do the backside attack. But if this were methyl, it would be able to. So, what happens is you can't get this substitution because the oxygen can't squeeze in to occupy the anti-bonding orbital, the pair of electrons occupying the anti-bonding orbital. So what happens is it can only bump into the sort of outside of the molecule. And if you look at this, this is CH3, CH3, CH3. So this back side of the molecule, it just looks like it's covered in protons. And so when O- comes in, instead of overlapping with the anti-bonding orbital, which is right in here, what happens is it bumps into one of the protons. And so it just plucks off the proton. That's what happens when it is sterically hindered. And of course, it forms an alkene. Let's go back and look at that. So here, the double bond will be formed right here, okay? Because you're going to lose the proton, the pair of electrons will move in. You're going to have Lg depart with this pair of electrons. So that pair of electrons will move in, form a double bond here, and the product will be isobutylene, okay? So alkenes are formed in these elimination reactions. They're given IUPAC names using the same procedure to name alkanes with minor modifications, This is going to be the first of many, many, many times that you are going to see a new family. You're going to have to learn the new family's nomenclature. And now this new family, remember how I said that in the alkyl halides, the halogen substituent was a prefix, and it was considered to have the same priority as the alkyl groups. Well, it's not going to be the same in the vast, vast majority of cases now, in the future. So for an alkene, where you have a double bond, in this case, the alkene is, you have the alkene family, and the double bond is a functional group, and that functional group has a high enough priority that it is not considered a prefix. It comes as a suffix. And so a 4-carbon molecule that has a double bond will be butene. So the ene is the suffix that is added. That's what you're going to see. So, and that's the same way that you're going to see it happen when you have alkynes or ketones or aldehydes, carboxylic acids. In those cases, the functional group will be designated by a suffix. Okay, so these alkyl halides are a little unusual. There are a few other families, but not that many. So here you identify the parent chain. So here the difference is that the parent chain must include the double bond. It must include the double bond. So it's going to be the longest alkyl chain that includes the double bond. So you have to remember that. And this will be the same when you go into name alkynes or ketones or aldehydes. The functional group, the highest priority functional group, must be included in that parent chain. So then you have to identify and name the substituents, just like before, the ones that are attached to that parent chain that bears the functional group. Then you have to assign a locant and prefix, if needed, to each substituent, and you have to number that parent chain in a manner such that the double bond has the lowest number possible. So, of course, here the double bond is going to consist of 2 carbons. You will only specify one of those carbons because you know that the other carbon is going to be next door. So you list the numbered substituents before the parent name in alphabetical order, just like before. You ignore the prefixes except for iso and also neo. There are a small number of these. The ones that do not have a hyphen after them and they are not italicized. When you order them alphabetically, the carbon-carbon double bond locant, the number that tells you where it is placed either just before the parent name or just before the -ine suffix. And I think it will be better for you to learn it when you're writing it just before the -ine suffix. But you'll want to be able to recognize the name regardless of where the number is. And you're going to see both of these in just a minute. So identify the parent chain. So here 5 carbons, it would be pentane, but the ane is replaced by ene if you have an alkene. The parent chain must include the carbon-carbon double bond, so this would be octane. If you put the double bond up here, then it's not going to be octene because the double bond must be included in the parent. So this will not be octene, this will be heptene because you're going to go this direction when the double bond is up here. So this is going to be propyl-heptene. So this would be 1, 2, 3 propyl, 1 heptene. You must identify and name the substituents. So here we go on our numbering again. The first thing that you have to do is to look to see where is your highest priority group. And in this molecule, it's going to be the carbon-carbon double bond, the alkene functionality. That's your highest priority. You have 1, 2, 3 methyls. So you must start numbering from the end that gives your double bond the lowest possible number. So this is going to be 1, 2, 3, 4. It's not going to be over here because this would assign the number 5 to your alkene, and that's incorrect. So this is going to be 1, 2, 3, 4, 5, 6, 7. So it's going to be 5, 5, 6 trimethyl 2 heptene. And so you don't have to say the 3 because you know that the other end of the double bond is on the next carbon. So you don't have to say where it ends. You just have to tell where the double bond begins. You list the numbered substituent before the parent name. I already gave that to you. 5,5,6 trimethyl 2 heptene, or you can name it 5,5,6 trimethyl hept 2-ene. Now this is going to be preferred and needed if you have a more complicated molecule, because let's say that you had a carbonyl right here at carbon 4. If you had a double bond O, then this would be a ketone. Okay, and the ketone would take a higher priority. So now you would number this. Well, it doesn't matter which way you number it because the ketone would be at the 4 position. So, but it would matter if you put the numbers here because what you would do is simply add O-N-E out here at the end, because the substituents are tacked on, the functional groups are designators are tacked on, so that the highest priority functional group comes at the end of the name. So if you had a carbonyl here, this would be 5,5,6-trimethyl-hept-2-ene-4-one. Okay? So that's why this is better, because if you tried putting them here just in front of the stem designator, you couldn't say 2,4-heptene-one, because you wouldn't know which one was the 2 and which one was the 4. So you have to say 2-ene-4-one. So anyway, that gives you an example. And also, the whole thing has to be prefixed by a designator that will tell you what is the stereochemistry here. And this, as you remember, is, you could name this one by either cis-trans or EZ rules. So this could be named trans. You could put trans in front here without the parentheses, or you can put the E in front with the parentheses. E for entgegen. And we've already covered that, so I'm not going to spend more time covering it. We've had this. Remember that what you do is you look at one end and you look at the other end. You see where the higher priority groups are. Fluorine has a higher priority than carbon. Nitrogen has a higher priority than hydrogen. The two higher priority groups are on the same side of the molecules. So this is zoosalmon. So this is going to be Z. And notice how they are indeed close. That's why the word zoosalmon was selected by Germans. So this is Z, this one is E, entgegen for across. The alkene stabilities, you can see this is a model of trans-2-butene. This is a model of cis-2-butene. You can see the steric strain here. So cis is going to be higher in energy than trans. Trans will be more stable. That's the other way of saying it. The difference in stability has been quantified by comparing the heats of combustion, because both of these molecules, when burned, give the same products, and the difference in the heat that's given off tells you that this molecule gave off more heat, therefore it contained more energy at the beginning. And here is just a plot that shows that. So this one had more energy at the beginning. This one was more stable. They were burned. They gave the exact same products. This one gave off more energy. That one gave off less energy in the form of heat. So, similarly, compounds, the stabilities of these compounds have been determined. So, what you will find is that the greater the substitution on the double bond, the more stable the alkene is. So tetrasubstituted is more stable than trisubstituted, and that's more stable than disubstituted, and that's more stable than monosubstituted. This is in the direction of increasing stability. So where is cis? Cis is right in here, because cis is just a little bit less stable than trans. And if you had both of these substituents on the same end of the double bond, so that would be gem substitution. So if you had the double bond and then both substituents coming off the same end, it occurs here. So cyclic alkenes with fewer than 7 carbons in the ring. Only the cis alkenes are stable. Why? Because the ring is just too small to be able to accommodate a double bond. Try making that with your molecular models. Try making these with a trans double bond in there. You'll see that you can't. Okay, you start breaking your models if you force it. So it's just too strained. It's impossible. So these are, of course, cis. When applied to bridged bicycloalkenes, the rule is called Brett's rule. So here this compound where this means that you cannot have a double bond at a bridge head if you have fewer than 6 carbons in the ring. So this compound is not stable. This compound is, because you've got 2, 4, 6, 8 carbons in the ring. So this molecule with the double bond at the bridge head is stable. Now for regioselectivity, what happens is when you react your branched alkyl halide with a strong base, and the base comes in to pluck off a proton and form a double bond, that double bond can be formed in multiple places. So what happens is the ethoxide can come in over here and pluck off hydrogen from a methyl or from this methyl. It can pluck off a proton from this CH3, or it can pluck off a proton from this methylene, from the CH2. If it plucks off a proton from the CH2, the double bond will be formed here. If it plucks off a proton from the CH3, the double bond will be formed up here. And you can see that these two methyl groups are equivalent. So you can form the double bond here internally. This is an internal double bond. This is an external double bond. So this is named the Zaitsev product, and this is the Hoffman product. Now the interesting thing about these is that you have 3, 6 protons that could be plucked off by the base to form this product. Here you have 2 protons that could be abstracted to give this product. So these protons are presenting themselves in a 1-to-3 ratio, 2 to 6. And so statistically you might expect to have the products formed in a 3-to-1 ratio, 3-to-1. But that's not what you see. What you see is a lot more of this internal alkene. And the reason is because this internal alkene is much more stable. And so that stability overrides the statistical effect. And so this is the regioselectivity of the reaction. And so this reaction, this particular reaction, with this strong base, if you change the strong base, you'll change these ratios. And so this particular one gives the regioselectivity of 71 to 29, because here we're talking about which region of the molecule reacted. Was it the protons out here at on the methyls, or was it the internal protons of the methylene? That's a regiochemical consideration, because you're talking about which region of the molecule, and here we're talking about which region of the molecule was the double bond formed in. So that's regiochemistry. It has nothing to do with cis or trans or ZE. It's just which region of the molecule. So this is a 1-butene. This is a 2-butene. Okay, that's the regiochemistry. And this is a regioselective reaction. So let's look at this. This is the reaction that we just looked at. There's the 71% and the 29%. The Zaitsev product, the internal double bond, and here's the Hoffman product. The external double bond, the terminal double bond. Terminal means it's coming at the end of the alkyl chain. And so what happens if you make this base larger? Okay, let's go back. So when the ethoxide comes in for attack, it can pluck a proton off of these terminal methyl groups, or it can come in and pluck a proton off of this internal methylene. If it does, it's going to have to squeeze in here around that methyl group, and that's a steric problem. So what happens is over here, now you've got this base that is so much bigger. So it's still easy for the base to pluck a proton off of these terminal methyl groups, but it's harder for this larger base to pluck a proton off of the internal methylene. And so you see this 71% drops to 28%. That reflects the steric hindrance about that internal methylene. And indeed, if you make the base even larger so that you're going to increase the steric hindrance at that position, it's still just as easy for it to pluck a proton off of these terminal methyls. But it's harder for it to get in here. There's steric hindrance. It's harder for it to get in and pluck this internal proton off. And so you see that the internal double bond is formed even less. So this really favors the terminal double bond formation, and that's purely a steric effect. Sterically hindered bases, okay? This is increasing the steric hindrance of the base. So now these are other sterically hindered bases. This one is an oxygen anion. This is an amine. That's an amine. These are others that you'll see. They are in your textbook in this chapter, and you just simply must learn them. And I think it's going to be obvious to you that if you have an isopropyl group, it's going to be more sterically hindered than if you just have a methyl. Same thing for if you have ethyls as opposed to methyls. You just have to be able to recognize that. So now that this, what we've been discussing all along is regioselectivity. As you increase the steric hindrance around these bases, you're going to increase the regioselectivity. Okay, that's the take-home lesson from that. Now we go on, we're talking about stereospecificity. It's an entirely different subject. It has nothing to do with what we just finished. It's in this section, but it has nothing to do with what we just discussed. So, but we are still on the E2 reaction. So not only do you have to consider the regioselectivity, you also must consider the stereospecificity. And the definition for stereospecificity is nothing like the definition for regioselectivity. So here, look at this alkyl halide. Once again, you have an alkyl halide, okay? An alkyl group bearing a halide substituent, But this alkyl group is much more complicated than what we saw in the previous slide. So what's happening is this is set up so that in order for the E2 reaction to occur, you have to have the leaving group, the bromide, which is going to depart as Br-, it's going to take that pair of electrons with it, and the proton that's going to be abstracted. The pair of electrons will move in and form the pi bond right here. They have to be on opposite sides of the molecule. Okay, you might want to draw a Newman projection of this. If you draw a Newman projection of this, the hydrogen will be anti to the bromine. And you need to be able to recognize that. So what happens is when the base, the strong base, comes in and plucks off this proton right here, the pair of electrons moves in and that moves in, what are you going to have? What products are you going to have? Well, if you look at it, you have the phenyl group coming out at you and this hydrogen coming out at you. So those are going to wind up cis to each other because they're both coming out at you. Here you have the methyl group going back and the tert-butyl group going back, and so those are going to wind up cis to each other. And indeed, here the phenyl and the hydrogen do wind up on the same side, and the methyl, which is going back, and the T-butyl, which is going back, do wind up on the same side. And that is because of this requirement that in order for ethoxide to affect this reaction, you have to have the hydrogen and bromide anti to each other. You cannot rotate this in the molecule around so that you might get that product. It doesn't happen. Okay? And so this is the explanation, to need to have the two groups that are leaving anti to each other in order to have the E2 reaction. And this E2 reaction, the fact that it is concerted is what requires these two bonds to be anti to each other in order for this reaction to occur. If you have like a cyclic molecule or something so that these two groups cannot be anti to each other, then you may not have the reaction occur at all. Or it may occur much more slowly through a slightly different mechanism. So here it is again. These four atoms must be coplanar, okay, in order for the reaction to occur. Okay. So there are two conformers here. They're called rotamers. Here, this shows you the need to have these anti-coplanar in order for the reaction to occur. Here, this is, if you rotate this so that you have these two cis to each other, or syn, and yet still in the same plane, the reaction could still occur, but it will be much slower because you don't get the good overlap like you do here. So now let's look at this. This is the Newman projection. You can see these two are anti and staggered. Now the syn coplanar, this is a higher energy rotamer. It's going to be have a shorter lifetime because this is actually a transition state. And so this one is going to be, if you push it, it can be observed, but it's much more difficult to get this reaction to take place. Okay, and let's go back and look at why. Let's look at why for just a minute. Why it is that you need these to be anti instead of syn. If you have the CH bond sticking up, notice that the hydrogen and the bromine are actually pointing away from each other. And this way, the CH bond going down and the CBr going up, notice how this bond is parallel to that bond. And what you have is, in the transition state, you have an incipient pi bond here, a partially formed pi bond. And you will remember that in order to have a pi bond, you need the p orbitals to overlap sideways. Okay, and so the p orbitals must be parallel in order to have good overlap. And so here, these bonds, which are going to give you the p orbitals to form the double bond, are indeed parallel. But if the hydrogen is going up, they're not parallel. They're pointing away from each other. And so you don't get the good overlap the way you do here. As this, remember, this is a single-step concerted mechanism. And so as this is leaving, that's leaving. And so you have the pi bond forming, and it's able to overlap very well as it forms. And so that's another reason why this is favored. the 180 degrees is not strictly necessary. You can still get good overlap. What it is pi bond. You can have a significant amount of strain, so you can have the orbitals twisted somewhat and still have a pi bond. And so that's what they're talking about here. They're talking about the amount of twist that can be permitted and still have a pi bond. And so you can still get overlap and the incipient pi bond formation, even if you don't have the exact 180 angle. They don't have to be exactly parallel. So the good thing about this is because this is a concerted reaction, it gave chemists the opportunity to set this up so that they would be able to synthesize less stable Z isomers, and it has been used for that. So here, this concerted reaction here will not always lead you to the more stable product. And here we're talking about Z and E. We're not talking about the regiochemistry. Remember, we're talking about stereospecificity. This is the stereochemistry. Z and E, cis and trans. Okay, more on stereospecificity of the E2. For this substrate, the beta carbon has 2 hydrogens, and you have 1 leaving group. So in this case here, this can rotate just a little, and you can still have the CH bond, the line up with the bromine, or you can have this CH bond line up so that you'll have good overlap. And so if you have, notice in this one, where you've selected this particular proton, R1 is coming out at you and R2 is coming out at you. And so that leads to this product. But if you rotate this so that the CH bond that's in back is down, that's going to make R1 go back, and this proton will come out at you. And so then when R1 goes back, it's going to wind up cis to R3 and lead to the other product. So you'll get this product by just rotating that a little. This particular conformation will lead to that product if you rotate this just a little so that this CH bond is going down instead. You'll get this product. If you can't see it on the paper, make your model and you'll see it there. So more on stereoselectivity. Consider the dehydrohalogenation of 3-bromopentane. 2 stereoisomers are possible products. So here you can get either the trans or the cis, like you just saw on the previous transparency. What happens is, because you have the product being formed, the higher energy product being formed, and it has to go through the higher energy transition state, because as the pi bond is developing, these 2 groups are coming in close proximity together. Here, as this pi bond is developing, the 2 groups are pointing away from each other. So you have this situation that I said earlier was most common. You have the higher energy transition state leading to the higher energy product, and here you have the lower energy transition state leading to the lower energy product. And that is the situation that you see. You'll have it 99% of the time. Higher energy leads to higher energy. Lower energy leads to lower energy. But there are a few situations where it's different, like we covered previously in a different video. So here we have stereospecific versus stereoselective. So the difference between stereoselectivity and stereospecificity, you're going to see stereospecificity and you're going to deal with it more. That's what we've been dealing with mostly, is the stereospecificity, where if you have one particular stereoisomer or, one particular stereoisomer, it leads to one stereoisomer. And if you have the its enantiomer or a diastereomer of it, it will lead to a different product.